right. We have come to a crossroads, right? I think we're on like discussion 34 now. We've come a long way. I'm proud of myself. Again, if you like this kind of content, hit subscribe, go onto my Patreon page and contribute. But I feel like we've come a long ways, right? I think we're done with like chapter 6 now, or maybe chapter 7. I can't remember which chapter the quantum mechanics ends at and quantum field theory starts. I think quantum field theory starts at like chapter 8. So we're on chapter 8, right? We've done 7 chapters in 34-ish videos. This is impressive. Now we're getting into quantum fields, right? We've had so many prerequisites. It's almost like, what's the point of going into quantum field theory? Well, there is a point. The point is to be continually proud of yourself that we can now understand more of this. Let's get right into it. What is a quantum field, right? We have been going over so many prerequisites. We haven't really gone over quantum fields yet. So what I'm going to do in this video is I'm going to give a big, broad overview of what the general prescription is going to be for these quantum fields and and then we're going to get into the actual content of the book, right? So what is the method that we use to develop quantum fields, right? So we've talked about classical fields. We've talked about classical spinor fields. We've talked about classical scalar fields. We've talked about the classical gauge fields, right? Electromagnetics, and so forth, right? And these were all described by Lagrangians, right? We've had our Klein-Gordon Lagrangian, we had our Dirac Lagrangian, we had our Proca Lagrangian, and all of these describe fundamentally different types of mathematical objects. And we had solutions to these Lagrangians also, right? So here's the Lagrangian, right? It takes some form. It's a function of position and velocity. And we have the actual functions themselves. That is a product of the Euler-Lagrange equations, right? So if we were given some Lagrangian, and here, what I'll actually do here, I'll erase this. We're given some Lagrangian, and we can do one of two things, right? We can say, well, we can go in this direction, right? So this direction, if we apply the Euler-Lagrange equations, we get our solutions, we get phi, right? So what is the actual form of phi given our Lagrangian? That's what we get through the Euler-Lagrange equations. And then we defined this thing early on also when we were talking about classical field theory. This idea that we can take the derivative of the Lagrangian with respect to its 0th component, right? This should actually be like that, and we call that the conjugate momentum, right? So what we have in our toolbox is this guy and this guy. Okay. And then so that's the classical field theory in a nutshell, right? Classical field theory says we can have these fields that are solutions to the Lagrangians, and then we can have their conjugate momenta fields, which are solutions to the derivative of the Lagrangian with respect to one of its variables, right? And we sort of established this before already. This was in some of the earlier videos that we talked about. Now I have this red line, right? We're now crossing over this red line. This red line is the boundary between the classical analysis and the quantum analysis. So we can take these two fields now, right? So this guy here, so that guy here and that guy there, we find their commutation relationship, and we say that that commutation relationship is, we essentially solve this, right? Such that it satisfies this condition. And when we do that, we get these relationships out for our fields. And these, we get other things, right? We can get other weird phenomena out of this kind of analysis. This right here essentially is putting our, so sort of casting our light into the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle is essentially quantum mechanics, right? This is the general prescription, right? Lagrangian, from the Lagrangian we can get our solutions. We can also get our conjugate momenta. Then we find the commutation relationships between our conjugate momenta and our solutions, such that we satisfy this condition. And when that happens, we get these relationships out. And we can do that for spinor fields, we can do it for scalar fields, we can do that for classical field, or we can do that for gauge fields, and that's what we're going to do. That's what this book is going to do. And yeah, that's the general prescription here. Let's take a look also at this very simple schematic, right? So we have, in one case, this is the value of the field, and these are the momenta of the field, or value of the fields, and then we have other values, right? So I'll just say momentum conjugate, momentum fields. These things are integrally related by this relationship right here, right? We take the derivative of our fields. Actually, no, we take the derivative of the Lagrangian, right? So this should be like that. And yeah, so again, what we're interested in is when we make these quantum, right? Essentially what you have to do is you have to say, well, we can't know the position and we can't know the momentum at the same time, right? That's what's quantum about quantum mechanics, or that's an aspect of what's quantum about quantum mechanics. Whereas in classical mechanics, you can know, right? So what you need to do is, right, you need the positions, right? You need the values, and you need the derivative of the values, right? That's sort of equivalent to your momentum. And then once you get those two things, you perform a commutation relationship with those two things, and you can get the weirdness of quantum field theory from that. But again, before we call it on this video, you have these guys, right? Whoops. You have these guys, right? These are the positions, if you will, and these are the momenta, right? Can't know position and momenta at the same time arbitrarily. That's, again, Heisenberg. So you take that relationship that you can't know them arbitrarily, right? You take that commutation relationship, and from that you get the dynamics, right? You get the logical mathematical consequences of that. And what we're going to find out is that this is going to lead us down a path of weirdness, right? Quantum field theory has its weirdness to it, right? It's weirder than quantum mechanics in many ways, because, well, for one, we're considering these fields, right? This thing that exists everywhere in space and time. And second is it's very non-intuitive, right? It's even more non-intuitive than quantum mechanics, in my opinion. But we can make sense of this slowly, which is what we're doing. And slowly but surely wins the race, I guess, right? We're I don't know what kind of race we're in, but we are chugging down this book. Again, the book is No Nonsense Quantum Field Theory, right here. Pretty thick book. It's a good book, though. I like it. And we are continually amazing ourselves with the nuances of quantum field theory. So with that being said, I will see you guys in the next video. Make sure to like and subscribe if this is the kind of content you like. Bye.